All right, good morning, Math 20-2 students. Today we're looking at lesson 2.6, so this is the last part of chapter 2 here, and we're going to be looking at proving congruent triangles. So if you remember in the last lesson, we looked at just kind of like an introduction to figuring out what congruent triangles are, and so you should remember that congruent triangles are triangles that are basically the same as each other. And we looked at 3 different proofs that you can use to identify that they are the same, which would be that they have 3 sides that are the same, so we call that SSS. Or you could look at side, angle, side, so where they have 2 sides that are the same and then the angle that's contained by those 2 sides is the same. I should have actually had that out here maybe for you guys. Oh, there it is. And so side, angle, side. And then the last one we looked at was angle, side, angle. And so this is where you have 2 angles that are the same, and the side that connects those 2 angles is also the same between the 2 triangles. So those are our 3 proofs that we can use in order to make congruency statements to show that different triangles are congruent. Okay, so today we're going to start out with a little bit of more of a review from the whole unit before we move into more information about congruent triangles. So in this first one we have sets of parallel lines. So here's the little arrows proving that these 2 lines are, or showing that these 2 lines, I guess, are parallel. And then we have a whole bunch of different transversals here. And so we want to go through and answer a few different questions. The first one says, which angle property proves that angle PYD, so I've already highlighted these so they're easy to pick out, is equal to 90 degrees. So how can we prove that this angle here is the square that I've drawn in, right, the 90 degrees? Well, if we look, we can see that this angle here is 90 degrees as well. And what is the relationship between these 2 angles? Well, hopefully you can see that because they're in kind of, remember we called corresponding angles as being in the same position. So basically, if we have our 2 parallel lines, both of these 90-degree angles are on the bottom side of the parallel lines and on the right side of this transversal. So they're essentially in the same spot. So we can say angle PYD is corresponding to angle, or corresponding, which means equal, with angle PWA is our other set of letters that connect that. So angle PYD is corresponding or equal with angle PWA on parallel lines. So that shows us that those angles would be the same. The next one we have here, which angle property proves that angle DAB is equal to 120 degrees? So angle DAB is this one here that I've kind of drawn in, and we want to prove that it's 120 degrees. Well, hopefully you can see pretty quickly that we have 120 degrees right over here, and what is the relationship between those 2? Well, we can say angle DAB is, hopefully you guessed this already, opposite, which means equal, equal to angle LAW. Okay, and let's see, the last one we have here, which angle property proves that angle BED, so this one where I've drawn the little angle in, is equal to 73 degrees. And again, we can see that 73 is filled in here, so we just need to figure out what is the relationship between this angle here and that angle there. Well, they're both on the inside of these parallel lines, and they're on opposite sides of the transversal, so we can say angle BED is, now hopefully you guessed this already, alternate interior. And again, that means it's equal with angle This angle we would say is angle EBC on parallel lines. Okay, so those are our different angle properties we can use for that set of lines. All right, the next one, what are the correct measures of the indicated angles? So basically, we're asked to solve for all the unknown variables here, so x, w, and y. Now, personally for me, I started out with, I thought 120 degrees directly opposite it, that is w. So that's nice and easy because then we know it's equal. So we can say angle w equals 120 degrees, and our justification for that is because it's opposite. Okay, now if we know that w is 120 degrees, what's the next thing we can solve for? Well, hopefully you can see that w and y together, because they sit on the transversal, are going to form a straight line, which means that they are going to be supplementary. So we can say angle y is going to be equal to 180 degrees minus w, which was 120 degrees. And that's going to give us 60 degrees. And that is supplementary. Okay, and then the last one we need to solve for here is x. So does x have a relationship with any of these angles? Well, we can't use the 120 because 120 is on the exterior and x is on the interior, so we can't use the alternate rule. But if we look at y is in the same position as x essentially, right? Because it's on the bottom side of the parallel line and on the left side of the transversal. So that means they have the relationship of being corresponding. And so then we can say that angle x is equal to angle y. And that is equal to, we said y was 60 degrees. And, whoops, I didn't mean to put in an equal sign there. So then we can use the justification that they were corresponding angles. There. Okay, another one. Let's just see here. I think this was the last one of our practice ones. Yep. So what are the correct measures for y, x, z, so this pink angle, and xzy. So xzy is this blue angle here. So let's have a look first here at y, x, z. How could we determine what this measurement would be? So if you want, you can pause the video, see if you can solve this maybe on your own first, and then come back and see. So we know that because angle x here is on a straight line with this 101 degree, it's going to be supplementary. So we can say angle x is going to be equal to 180 degrees minus 101 degrees, which is going to give us 79 degrees is going to be our angle x. And the reason for that was because they were supplementary. Okay, what about angle z here? Well, we have this angle y is 64. We just solved for angle x as 79. The shape that we have is a triangle, so then we can use our angles in a triangle adding up to 180. So we can say angle z is equal to 180 degrees minus 64 degrees minus 79 degrees, which is going to give us 37 degrees. And the justification for that is that angles in triangle equal 180 degrees. Okay, so there's our solution for that triangle. All right, let's have a look at moving on to this new information, which is talking about proving congruent triangles. So if you want to complete a formal proof that two triangles are congruent, you have to show that the corresponding sides and angles in the two triangles are equal. So basically, we're taking what we learned last week about how you can use those proofs, and using them to show that different triangles are congruent. And then we'll be kind of moving through, again, questions with increasing difficulty. So for example, this first one here looks pretty similar to something that we did in the last lesson. So it's not going to be super tricky because we can see that we have angle S here. Now, if you want, you can go ahead of me, maybe pause the video, see if you can pick out which angles are going to be congruent with each other, or the same as each other, I guess, making the triangles congruent. Okay, so if you come back to the video, you should see angle S and angle F are equal. Angle X and angle Y are equal. And then we have this one tick for the sides SY and XF. And so those are going to be the same as well. So we've got same side. And we've also got same angle here. Okay, now I mentioned to you last time, I'm not sure why I'm not seeing this so much in this textbook, but I mentioned to you that sometimes, like usually what you would see, at least in my experience in geometry, is that if these two angles are the same, you would have to differentiate them by putting like one little tick like this. Some of the questions in the textbook don't seem to do that, so I guess you can just kind of assume that they're going to be the same for questions like this. But usually what I've seen in the past, because you wouldn't want to think like this angle is equal to that angle, even though visually it's obvious that they're not. But what I've always seen in the past is that they'll make like a marking on the two that are the same so that you don't confuse them, especially if they're kind of like closer angles. In this particular example, it's fairly obvious, but okay. And the other thing is, remember that when you use the angle side angle argument, the side that has to be the same has to be contained by the two angles that are the same. And so we can see that that condition is met in this particular set of triangles. So we can go ahead and use that proof of angle side angle. So let's maybe start with angle S is equal to angle F. And so that's going to be our angle argument. Then we want to go side, right? Because we want to go angle side angle. So we're going to do SY is equal to FX. And you'll notice that I'm putting them in the same order, right? So if you're going from the yellow, like the same angle here, over here, when you list your side, so it's going from S to Y, then you want to do the same thing in the other triangle. So in that case, going from F to X. Okay, now the last angle that we had was, oh, and I also want to make sure I start with this one. Okay, so angle Y is equal to angle X. So that's another thing to kind of be aware of, is when you're listing your proofs, you usually want to make sure that you're always doing the same comparison. So if I started by comparing an angle in this triangle to an angle in that triangle, then I want to do that for the other, like the sides as well, starting with this one, comparing to that one, just for consistency's sake. Okay, and so because we have those equal sides and angles, we can say, therefore, triangle SYL is congruent to, so remember that little sign, triangle FXO. Okay. All right, now let's move on to one that's a little bit more complicated. So in this one, we're given some facts about this triangle, and then we're asked to prove that triangle TAC is isosceles. So basically TAC is this whole big outside triangle, even though it's divided in these two smaller triangles. So the first thing you want to do with questions like this is make sure that you've identified what are the given facts. So first of all, we're given that TP is perpendicular to, so this little sign here means perpendicular, and you should remember from previous learning what that means in terms of an angle, which means that it's 90 degrees, right? So if it's perpendicular to AC, which is here, that means we know that this angle here is 90 degrees, and of course, because they're on a straight line, this angle here is also 90 degrees. Okay, so The other thing we're told is that AP, so from A to P, is equal to C to P. So basically that means that this length is equal to that length. Okay? And we're trying to prove that TAC is an isosceles. So if you remember, we mentioned isosceles earlier in the unit, and an isosceles triangle is one that has two equal sides. Okay, so basically that means that if we look at this TAC, we're going to have two sides that are equal to each other. Now, just by looking, it's probably pretty obvious which two sides you would want to say are the same. This side, you wouldn't be saying like this side AC is equal to TA here, but instead you would be saying TA is equal to TC, right? So with isosceles, it's usually pretty easy to see the two sides that you're trying to compare. So essentially, we want to prove that these two sides are equal to each other. Okay. Now, one of the ways that we can do that is essentially if we look at these as two smaller triangles, what we already have with these two triangles is one side that's equal and an angle that's equal, right? So if we think back to our list of proofs that we can use, if we already have a side and an angle, then remember that the next side we can check for that would be the same has to be one that's on the other side of that angle. So basically it has to be side and then angle and then the attached side, right? So we couldn't use that side over there. And so if we look at this triangle, we have side, angle. Now we can't prove this one because it's not connected between the side and the angle. So the only thing we can prove is this side, which is actually pretty easy because it's the same side for both triangles, right? For both of these little triangles, they actually share that side. So of course it's the same for both triangles. So now we can prove that side is the same, angle is the same, side is the same. After that, we can move into looking at our proof. So let's go through and just prove that these two triangles are congruent. So the first one was side, which is AP is equal to CP, and that was just given to us. Then we also have angle APT is equal to angle CPT. And that's our angle argument. And then the last one is side, which is going to be PT equals PT, which is pretty obvious. So that's side. So then we can say, therefore, triangle APT is congruent to triangle CPT. So CPT, right? Now, we need to think about the logic of what that means. If these two triangles are congruent, we've proven it just using this side, and this angle. But what that really means is that all we needed was those sides and that angle in order to prove that these triangles are the same in every way. And so now we know that if these triangles are congruent, their other side, their remaining side that we haven't proved yet, also has to be the same. And so basically what we can say is, because triangle APT is congruent to triangle CPT, corresponding sides are equal. So corresponding sides, in this case, it's AT and CT are equal. And that's exactly what the definition of an isosceles is, right? That it's going to have these two equal sides. So when we look at this as one big triangle, these two sides are going to be equal, even though we proved them using the two smaller triangles. And so now we can say AT equals CT. So so triangle TAC is isosceles. Isosceles. Okay. All right, let's move on to another example here. 2.6. Okay. So the next example we have here is given that AE and BD bisect each other. So this is a new bit of terminology. When we see the word bisect, you might recognize from the different like kind of Latin roots to the name. Bi means two, and then sect, right, to cut. And so basically what bisect means is that you've split equally in half or exactly in half. Okay, so that means we have two equal pieces on either side. Okay, and so if we look at what that means, AE, right, so going from here to here, and BD bisect each other at point C. So that means they've cut each other exactly in half at point C. So AE is cut in half by BD, right? And if this whole line is cut exactly in half, what does that tell us about these two sections? Well, it tells us that they're equal. So we can start out by saying, okay, AC is going to be equal to CE. Now, AE also bisects BD at point C. So that means that this line BD is cut into exactly two equal pieces. So we can do this because those two parts are going to be exactly the same as well. Okay, so basically now we can say AC equals CE and BC equals CD. Now what they want, and then the other thing that we're given, so we're given that they bisect each other, and we're also given that AB equals ED. So AB is equal to AD. So we actually have another set of same sides. And they want us to prove that angle A, so right here, is equal to angle E. Okay. So, of course, what we want to do then is try and prove that these triangles are congruent so that we can prove that the angles are the same. So looking at this, we can see that we have same angle and then same line, and then branching off of that one, going opposite directions for the different triangles, we have a side that's the same length as well. And then going down and connecting those two sides, we have another side that's the same. So the sides are equal and they connect in the same way with each other. So we can see that this triangle is congruent. So we just need to write out our proofs, which is AC is equal to CE, and that's side. Then what else do we have? We have BC is equal to CD. So that's side. Okay, and then BC, CD, and then the last one that we would have is AB is equal to DE. AB is equal to DE, and that's also side. Okay, and so now we can say we did side, 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 so we can say therefore triangle ABC is congruent to triangle EDC. Actually, I guess that'd be CDE, but oh well, for now we'll leave it as that. And so now if we, again, just like in the previous example, because we can say that these two triangles are congruent, we can say that their corresponding angles have to be equal. So because the triangles are congruent, corresponding angles must be equal. Corresponding angles are equal. Okay, and so then we can say, so angle A equals angle E. Okay, want one more. I think this is our last one actually. So we have the main entrance to the Louvre in France is through a large pyramid. The base of each face is 35.42 meters long. So I've already kind of sketched out what the pyramid is going to look like, because I didn't want to put you guys through the pain of watching me try to draw that. So essentially we have a pyramid, right? So it has like a square or rectangular base, and then we have like the points coming up from there. And the base of each face is 35.42 meters long. So we have the lengths of each side at the bottom are the same, right? So basically we could, in terms of triangles, we could think of it like this. The other two edges of each face are of equal length. So if you think about one face here, then basically we're saying the other two edges are of equal length to each other. Now this is maybe worded a little bit awkwardly, because you might think that that means that they're of equal length to the bottom. But I believe what they're actually trying to say is that these two sides are of equal length. And what they're asking us to do is prove that the two base angles on each face are equal. So basically that this angle would be equal to that angle, right? So we kind of have the same thing here again, where we're trying to figure out if these triangles are congruent, and then we can use congruency to prove that different components of the triangle are the same, essentially. So in this case, these base angles. So what we already have here is this side and this side of these two triangles are the same, right? They're 35.42. So let's maybe put in, let's call this A, maybe B, C, and D. Let's do that. So we can say side AD is equal to side CD, because we are given that. So that's going to be a side. Now the other thing that we were given is that all of these basically like sides here are going to be the same. So actually I could put one here as well. So comparing these different triangles, I could say side AB is going to be equal to side CB. AB is going to equal to CB. And then the other thing would be, the only thing connecting these two triangles is this same side. So it's the same for both, obviously. And so we can say DB equals DB, because it's a shared side for both triangles. And so we've done our side proof. And so we can say, therefore, triangle ABD is congruent to triangle CBD. And so now if we can say that these two triangles are congruent, then essentially if we're looking at these base angles even all the way around the pyramid, we can say, because the triangles are congruent, I'm going to use some shorthand there, corresponding angles are going to be equal. And so then we can also say, because the triangles are isosceles, right, because they have the two sides that are the same, so we know that they're isosceles. And if you remember, when we talked about isosceles a couple sections back, we mentioned that if those two sides are the same, the angles at the bottom of them, the angles at the base, are going to be equal as well. So we can say, because the triangles are isosceles, the base angles are equal. Okay, and so basically that's like, if you have an isosceles like this, then your base angles like that are going to be the same as well. Okay, so that's everything for proving Sorry guys, microphone keeps cutting out. So that's everything for proving congruency in triangles. And that's the end of chapter 2. So when you feel prepared, you can go ahead and write the chapter 2 chapter test. And then, yeah, we'll be moving on to the next section. So I'll see you there.